Hello, my name is Lucas Miners, and this is going to be my presentation on the Fibonacci sequence. Um, to get us started, we're going to maybe asking what is the Fibonacci sequence? And basically, it's a series of numbers where each number is the sum of the two preceding ones, starting from 0 and 1. Uh, so you start off with 0 and 1, and then 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 3 is 5, and so on and so on. And this continues infinitely. This is an example of a recursively defined sequence, meaning that each term depends on not just the two previous ones, but just the two previous terms. Um, this pattern appears frequently in nature, art, architecture, and even financial markets. There's kind of a visual representation of the Fibonacci sequence. You can kind of see on the left kind of how the numbers add up and you get each of the next one. And then on the right, you see this kind of spiral shape, and this is kind of the shape that you see appear oftentimes in nature. A brief history of the Fibonacci sequence. It was introduced to Western mathematics by Leonardo of Pisa, also known as Fibonacci. He used this sequence to model the growth of an ideal rabbit population. And although he popularized it and it's named after him, this sequence was previously known in Indian mathematics, dating all the way back to the 6th century. Over time, it became a fundamental concept in number theory, algebra, and natural sciences. Why is it important? It appears in many mathematical contexts, such as combinatorics, algebra, and geometry. Um, it also gives us the golden ratio, which is approximately 1.618. And this ratio has applications in design, aesthetics, and optimization problems. In nature, it can be found, patterns of this Fibonacci sequence can be found in sunflower seed arrangements, pine cones, the shape of seashells, hurricane, and even galaxies. And then many real world structures, including the Parthenon and Leonardo da Vinci's Vitruvian Man, are based on Fibonacci portions. It's an example of a recursive formula, which you can see with this f of n formula. Basically, that this means that if you want to calculate any Fibonacci number, you just have to know the two previous ones. So an example is like if you want to find the fifth one, it equals 5 and f of 6 equals 8. So in this, that gives you f of 7, which you just add up, and that gives you 13. Um, the best cases, the sequence starts with f of 0 and f of 1, and that kind of can get you going and it sets a foundation for generating the rest of the sequence. It's also a linear recurrence relation, meaning it follows a specific repeating rule so that it has a specific numbers are in the sequence. Um, you can also figure out how each term is derived. You follow you start at the beginning and follow the pattern of adding the two previous numbers. So, for example, f of 7 equals 13 because f of 5 equals 5 and f of 6 equals 6, and you add those and it gets you 13. Same for the previous f of 6 equals 8, f of 7 equals 13, so f of 6 equals 8. So 8 plus 13 equals 21. This rule allows you to generate an entire sequence indefinitely. It can also be calculated using matrix exponentation or Benet's formula. The relationship between consecutive terms, it gradually gives towards the golden ratio the more you go up. So if you divide the term by its previous term, the further you go up, the closer you get to 1.618. This long drawn out number. As you can see, like 20 or f of 8 over f of 7 equals 21 over 13. And as you go up, it progressively gets more and more. And as you approach infinity, the ratio stabilizes. This property explains why Fibonacci numbers often appear in nature and as naturally occurring growth patterns tend towards the golden ratio. And then a cool trick about maybe not trick, but cool little fact about the Fibonacci sequence is that each number is divisible by 2 and every fourth is divisible by 3. So, and then every fifth is divisible by 5. And so the results from the modular arithmetic properties of the sequence, this results from, and these properties are used in cryptography and random number generalization. Um, Here's a couple examples of the Fibonacci sequence in nature. One example is in flowers. So examples is in lilies, there's three petals. In buttercups, there's five petals. I'm not sure. I'm not even going to try to pronounce that, but it's 21 petals. And daisies often have uh, different Fibonacci numbers as the number of petals. So this arrangement maximizes exposure to sunlight and optimizes packing efficiency for seeds and pollen. The I don't know how to say that, but the leaf arrangements follow Fibonacci numbers to avoid overcrowding and ensure distribution. Another example would be pine cones, pineapples, and sunflower seeds arrangements. So sunflowers display seeds and spirals that follow Fibonacci numbers. So if you count the spirals in one direction, you might get 34. In the opposite direction, you might get 55, which are both Fibonacci numbers. And this arrangement ensures maximum packing density, meaning more seeds can fit on the flower head. Same thing goes with kind of with pine cones and pineapples also exhibit these spirals. If you count the spirals on a pine cone or the diamond-shaped patterns on a pineapple, they often come in 8, 13, or 21, which are also Fibonacci numbers. And this pattern helps maximize growth and efficiency and space utilization. And then the last real world example is going to be animal patterns. Um, Many natural spirals formations allow the Fibonacci sequence and golden spiral. So if you think of like a nautilus shell, as this grows, the shell expands following a logarithmic spiral based on the golden ratio. So if you find a shell in nature, you may notice that like it kind of wraps in on itself, and this is and that wrapping on itself would be that golden ratio spiral. Same with ram's horns and elephant tusks. These growth of these structures also follow Fibonacci expansion. So um, if you remember from the previous example, that spiral, if you kind of let their horns like grow out, eventually it'll just grow and start curving into that spiral. And then and even in galaxy arms, the spirals of galaxies, including the Milky Way, um, often conform to a logarithmic spiral based on the golden ratio. These structures follow the most energy efficient way to grow, which is why nature often uses the Fibonacci sequence, Fibonacci pattern. Um, it's the most efficient way, naturally these happen just in nature. And here's kind of a low definition example of what I was talking about. So in the top left, you have the sunflower, and you can kind of see, I mean, it's hard to see with this quality, but if you look at the seeds, you can kind of see, and then I'm not sure what this top middle one is, but it has the spiral. The top right one is a shell, and it wraps in. Um, you can kind of see it in this galaxy. Um, and then this flower over on the right. Even in DNA, even inside humans, there's often Fibonacci sequence spirals. Um, and then another shell, and I think this one in the bottom right looks like a storm. So, I think I said previously, hurricanes they follow this. So, are you there goes my timer? All right. Um, so shoot, let me share my screen. Okay. Don't know if that messed up my recording or not. I guess we'll have to find out. But yeah, so appears in hurricanes, spirals, all over in nature. Honestly, pretty fascinating that it appears like everywhere in nature. Um, so yeah, that's my presentation on the Fibonacci sequence. Hope you guys found it interesting. Thank you.